Now I think it's worth it to just spend a few minutes understanding the different shapes of both the input and the output, as well as the weights and the bias. So let's jump to Conv2D. And I'll start with the weights here. You can see that the shape is output channels, input channels, groups is 1. So output channels by input channels, then the kernel size, first index, and then the other kernel size. So this matches the shape of our weights. You see output channels, input channels, and then the kernel 6 by 6. And then the bias has basically just the output channels, because you're going to be adding the bias term to the weights for that channel. And we'll do a quick example in the next video. But basically, this is the shape of the weights, and this is the shape of the bias. Now, I think it's even more interesting to focus on how the input tensor gets converted to the output tensor. And for that, we're going to focus on basically this formula right here. And these are the parameters that we're going to be using. So I've inserted this formula right here, where our input tensor is the batch or number of images, the input channel, and then the input height and input width. Here is denoted with N. Very often you'll also see B for batch, but you can see here that N is the batch size, and C denotes the number of channels, and then the height and the width in pixels. So the output tensor will be the batch size, and then the output channels, as well as the output height and output width. So the output height and output width is calculated with this formula, where we have the input height plus 2 times the padding. You can see is indexing the first one because we're calculating for the height and the width. But if we focus on one dimension, let's say the height, for example, is the input size plus 2 times the padding minus dilation times the kernel size minus 1. And then that multiplication is minus 1 divided by the stride. And then to that, you add 1. These brackets here, this denotes the floor division, meaning the lowest integer. So if we have a decimal value, then we will round to the lowest integer. If this was on the top, it will be the ceiling division, which will round to the highest integer. In this case, we're rounding to the closest lower integer, performing the floor operation. Now let's print our values first here. So we have our input shape of 1 by 3 by 640 by 640 and 1 by 64 by 320 by 320. Nothing new here. This is basically the input shape and then the output shape, as we've seen before. If I extract the values for the height and the width, as well as padding, dilation, kernel size, and the stride, and then print them here, and then if we apply the formula with these values, we'll obtain 320 the output height, and 320 the output width, which is what we already knew was the correct value. Now this formula is the one that we have here in our PyTorch documentation, but I think it's more complicated than it should be. So how can we simplify this formula? If you see this term dilation is better explained visually. So you can see a normal convolution, which basically has dilation of 1, and then the same kernel, but with a dilation of 2. So it's still 3 by 3, but the kernel is being inflated, is being dilated. I haven't seen dilation used much, but of course it's a variable that you can leverage. We can also see it here as well in these papers with code. Looking at the convolution documentation, if we go all the way to the bottom, we can actually see another representation. So in this case, we're convolving a 3 by 3 kernel over a 7 by 7 input with a dilation factor of 2. You can see that the 3 by 3 has been dilated. So now we're jumping every other pixel, both horizontally as well as vertically. And then with the stride 1, you're going to jump 1 pixel to the right, as you can see here. And then the next one 1 pixel to the right. And then you cannot go any further on the horizontal. So then, given that the stride is 1 in both dimensions, then you'll jump right here, similar to this one, but 1 to the bottom, as you can see here. And then you continue to the right one more and one more to the right. And then you'll go 1 to the bottom and then 1 more and 1 more. And that will be the result of the convolution. But in the case where convolution is equal to 1, meaning nothing is different in that case, then this formula can be greatly simplified. If dilation is equal to 1, then -1 times -1 is 1, minus 1 is 0. So dilation cancels out. So dilation goes away, that -1 goes away, that -1 goes away. You have basically Win plus 2 times the padding minus the kernel size divided by the stride plus 1, as you can see here at the bottom. So in this case, the dilation of 1, which is in our case, by the way, cancels out, and then the formula is greatly simplified to something that you can actually more intuitively understand, where the width gets padded, and then you apply the filter to that. And if your stride is 1, then the output image won't change much. But if your stride is 2, the output image will be shrunk by a factor of 2. And then you add this plus 1 at the end, same as above. And then if we run this, the result with this simplified formula is exactly the same because our dilation is equal to 1, but it's greatly simplified. And in this case, to show you a different way of obtaining the same result, I'm casting the result to an integer, which is the same result as if we're performing the flooring operation with the math library. And just to print it one more time, our input image of 1 by 3 by 640 by 640, now we know mathematically, based on the values of the padding, the kernel, sometimes referred also as the filter. So if you see K or F, they're equivalent, as well as the stride. So as long as we know the input size of the tensor, and we know the padding, the kernel size, and the stride, we're able to calculate mathematically the output tensor, which in our case is 1 by 64 by 320 by 320, which again corresponds to the bad size, which doesn't change, the height and width of the output tensor, which we just calculated right here, as well as the number of output channels.